Hello, and welcome to the final presentation for our Intel 8080 emulator. Our group went about emulating one of the first microprocessors that started a new generation of computing, the Intel 8080 microprocessor. We accomplished this with C++ and SDL to fully recreate the experience of playing Space Invaders on the arcade cabinet, including historic color matching and gameplay speed. While in its current state, we have not tested any other ROMs, but the emulation was fully implemented with the entire instruction set. With some tweaking, this implementation will be able to load and run any program that was designed for the Intel 8080. With emulation, we are able to create an accessible archive of gaming history while also keeping the source code original. Now, I will jump to a short demo of our emulator by playing Space Invaders. Hello, welcome to Space Invaders. Here is the main menu where we are able to add credits with the C key. You can see credits are incrementing. We are able to play in either 1 or 2 player mode by loading a sufficient number of credits and pressing 1 for 1 player or 2 for 2 player. I will go ahead and showcase 2 player mode. Here we are able to play with either the arrow keys, the WASD keys, as well as the spacebar for firing to give players plenty of options for input. I'm going to go ahead and let player 1 die to show player 2. We will start with a fresh playing field, and player 2 uses the same controls as player 1. I'll go ahead and let player 2 die as well. When we switch back to player 1, we're going to pick up where we left off since the game state is saved in a specifically mapped section of memory with our memory implementation. Go ahead and let player 1 die. And as fun as it would be to keep playing this classic, the presentation must go on. So to exit, we can either press the Q key or escape to close the emulator. Hello, my name is Joshua Benge, and here are my contributions to the Intel 8080 emulator. First, I wrote the CPU class, and this class acts as the orchestrator for all of the other components, including our interrupt handler, memory implementation, input handler, sound mixer, and the shift register. All of the 8-bit registers such as the accumulator and flags byte, as well as the 16-bit registers, the program counter, and stack pointer, are implemented as attributes for a CPU object as shown below. Booleans are utilized to orchestrate the interrupt process. The public function step is used to read the next byte of memory pointed to by the program counter, which is then interpreted by a switch statement to execute specific opcodes. Here is some code highlighting the state of the CPU and pointers to its shared components, as well as showing the flags and registers and being implemented with structs to group together CPU state while making everything easily accessible. Next, I wrote the memory implementation that gave the Intel 8080 its accessible memory as described in the programmer's manual. This was implemented with an array with read and write methods that included restrictions for writing to read-only memory, as well as restricting the amount of loadable bytes. This ensures the emulation is kept true to historic hardware. Here is some code that highlights the class method definitions for memory, as well as the implementation of the load ROM method, the first step to starting the emulation. Most of the memory methods that are defined are not actually used in the emulation, but were utilized and modified to be able to debug and execute unit tests. Finally, I implemented the opcodes and instructions. Initially, my plan was to utilize an array instead of a massive switch statement for opcode implementation, but quickly realized that it would be needlessly complex. So, as a team, we decided to use a switch statement for the final implementation of the opcodes. After the CPU step method is called, it takes the byte of memory and passes it to the execute method, where the read opcode is interpreted and then executes the specified instruction with the specified registers or memory. An example, as we can see in opcode 0x01, the CPU will run the instruction LXI on the register pair BC. To emulate this, we will read the next 2 immediate bytes of data from memory, pass pointers for registers B and C, and the 2 bytes of data to the LXI function. Since the Intel 8080 is little endian, the most significant byte is the second byte of immediate data, and the least significant byte is the first byte of immediate data. So after that opcode is ran, register B will contain the value of the most significant byte, and register C will contain the value of the least significant byte.
David here. I wrote the input handling code, which used SDL3 event polling, as well as its library functions to identify key presses down and up. These were then used to set bit fields in a struct, which emulated the transfer of data from peripheral devices. And I wrote interfacing methods that worked with the input instructions that the 8080 would call and execute. I implemented some opcodes using Josh's generic instruction methods. I wrote debug helpers for tracing execution, included in a debug make target. I wrote the skeleton of the main loop with interrupt handling, and that was where we integrated all of our different code. I added a green color layer for the bottom portion of the screen, which simulates the arcade cabinet's own green filter, which would change the color of the 1-bit black and white CRT display. I helped with translating video memory to the game window display code, which Patrick had written. And then I set up doc tests and wrote some early unit tests for instructions. To showcase a bit of the work I did, towards the end of our development process, we suddenly created a bug. We had learned that we needed to implement auxiliary carry for another instruction we did not expect to be in Space Invaders. And suddenly, adding a credit increased the count from 0 to 7 instead of 0 to 1. Here's a screenshot from our Discord where Pat was showing that he had identified the issue, and it was this DAA instruction. Computer archaeology has the subroutine here for updating the number of credits, and the DAA instruction uses the accumulator to do binary coded decimal addition. So let's take a look at that function. In this first condition block here, we know that the accumulator, specifically the lower 4 bits, is 1 at this point in execution, which is not greater than 9. So the auxiliary carry bit must be 1. We also know from the debug printout that the carry flag was not set either. So that's our culprit, right? It's increasing the accumulator register by 6. And so add increases it by 1, DAA adds another 6, that's 7. So the auxiliary bit is being set correctly first by the comparison with of an immediate data with the accumulator, but then it's not being cleared by the add instruction. And the reason for this is that the subtraction version of the auxiliary carry bit update logic was being used instead of the addition version. So I went ahead and consolidated that logic into 2 distinctly named helper functions, one for add on the top here, the other one for subtraction on the bottom. Plugging those into those methods among the other methods that needed to update the auxiliary carry bit fixed the issue.
Hello, I'm Brandon, and I will briefly go over my contributions for this emulator project. I implemented the audio mixer that emulated the external analog circuitry from the original arcade cabinet. So I effectively had to create all the sound effects that the original analog circuit had handled. And here's just a couple examples of that. It was instructions out 3 and out 5 that triggered the sound effects based off the data loaded inside the accumulator register. And each bit in the 8-bit accumulator represents exactly one sound that could be played. I also worked on the shift register. The Intel 8080 on the original game actually used an external shift register to aid in the shifting of the video pixel data. It effectively did this just by passing 8 bits into the shift register via instruction out 4, and then instruction out 2 would set the shift offset, and then it would be fed back into the CPU via the in3 instruction to get those shifted bits back. Along with this, I also did a bit of debugging, and I helped track down a small handful of opcode implementation bugs. And also I implemented CPU cycles-based game loop. So effectively, each game loop iteration was capped at a set amount of instruction cycles, and this ended up being around 33,000 cycles for the original arcade cabinet. And below are the graphics for our original time approximated approach of the game loop and the CPU cycles based approach. On the left here, it's the game is running much faster and is actually quite difficult to play. And then on the CPU cycles-based approach, you can see the game is running much more slowly and a bit easier to play.
Oh, this is Pat Keleher. A couple of my big contributions to the team included the rough-in of the game graphics display module. That module came with functions to create and tear down the game window, as well as 2 functions to update the top and bottom half of the game window. Additionally, I had gone and encapsulated the VRAM memory map parsing functionality into its own little subclass or module. When it came time for integration, David had incorporated the graphics display module into the application and refactored it to fit our new strategy for game loop execution. Once that was in place, I debugged and refactored the graphics display in order to get the game output to properly display. The next big contribution I had was resolving integration address issues. So one of those was related to the RST interrupt service routine instruction, where we were popping address off the stack in the wrong order. Once I brought that to the team and showed the team the issue, Josh knew immediately where to go and implemented the fix for that, which resolved program execution issues inside of the interrupt service routine functions. The biggest contribution I had during integration was resolving our uncontrolled game restart bug. And the 2 pictures on the right here show exactly the issue we're facing, right? So we had a opcode return if 0 get called here, and that would effectively pop addresses off the stack, but it was popping the address off into the program counter in reverse order. So this program counter should actually have been 026F instead of 6F02, right? But when we pop the wrong address into the program counter, we increment, and we are just outside the bounds of the actual program. And we get all the way up to FFFF, roll over to 0, and restart the game. And the issue here was just fundamentally because calls and returns push and pop addresses onto the stack in a different order than pushes and pops do. And I discovered a case where we actually push an address onto the stack and then call a return to pop it off. And so the strategy conflict there caused us to actually just have the address populate in the program counter in the wrong order. So I implemented a fix for this inside of the XHTL opcode function. And once that fix was in place, the program counter no longer gets populated with the incorrect address, and thus it no longer rolls over, and thus we can play the game. And so those were my major contributions for the project.
In conclusion, this project will more than likely end here. There aren't any commercial applications for this without treading too far into copyright infringement. Further development might entail testing more ROMs as well as fixing minor bugs here and there. But as it stands, this was an excellent learning experience for us all. But it is, in fact, game over.